start out, I'm not used to using a mic, by thanking the organizers for doing all the work of setting this whole thing up, which I know was enormous, and for inviting me to talk about one of my favorite subjects. And I thought I would start out by telling you what I feel are maybe my top 10 reasons for thinking that tight closure is a good thing to study. Now let's see. So I'll do these in reverse, starting with the 10th. Now, you may think this is odd, but ever since Penn State joined the Big Ten, people at Big Ten universities have had a lot of trouble with 10 and 11. So one nice thing about tight closure is that it shortens hairy proofs. Proofs that used to be 40 pages become 2 sentences, as I'll try to show you. And in some cases, it's not always quite the same theorem. Sometimes it's a better theorem. It's maybe incomparable. But it does certainly shorten proofs. Now, this next statement, maybe if I thought about being videotaped in perpetuity, I wouldn't say this, but oh well. There's a question mark there. No, that's not true. It just makes them scratch their heads. Because results that seem to be analytic in nature and were first proved by analysis suddenly are being proved by characteristic P methods, which are probably as alien to the analysts as things like integrals are to me. Anyway, so that's number 10. Number 9 is that, and it's related to this, it can be used to prove the Briançon-Skoda theorem, which I'll tell you about in the course of time. And it can be used to prove that rings of invariance of linearly reductive groups are Cohn-Macaulay. And here, I'm trying to pick some things. These theorems don't involve tight closure in their statements, right? And several of them were proved before tight closure existed, or at least had been defined. It can be used to prove various local homological conjectures. And by the way, not only does it give new proofs, it gives new insights, and it strengthens the statements in many cases. So number 6 is it eliminates unsightly cohomology. Actually, with a little help from the Jacobian ideal, which annihilates that certain cohomology as a consequence of tight closure theory. Number 5. I think I wrote down makes theorems vanish. But that was just a sort of a little joke. It makes vanishing theorems, which are theorems about vanishing rather than theorems that vanish. English is slightly ambiguous. So it makes what I'm going to call contracted extension bulge manageable. And you have an ideal in a ring R, and then you have an extension ring S, which probably nobody can read this, but it's supposed to be module finite. Is that too small? Okay. Well, anyway, module finite. And then you worry about what happens when you expand I to S and contract to R. You get something typically bigger than I. What is the extra stuff? Well, tight closure gives you a handle on that problem. And you don't even need module finite. It turns out it's enough if the extension preserves height. So you get some very nice results of this type. And I'll mention right here that this also implies, these results imply splitting theorems. Another nice thing is it controls your colon ideals. Things like this, where the x's are part of a system of parameters. When these things are a regular sequence, you will just get the ideal generated by the x's. But typically, you get something unknowably bigger, but you hope not much bigger. And tight closure gives you control of how much bigger the thing you're getting is. So that's another application of it, and it's closely connected with several of the other things that I've mentioned. And I mean, at the same time that it's controlling your colon, tight closure compensates for failure of regularity. It's all in the mind of the beholder. So, of course, I'm talking about, one of the friendliest environments for a commutative algebraist is a regular ring, right? And lots of things work in regular rings that don't work in other rings, but sometimes you can make them work with a little help from tight closure. And what I have listed as number one is tight closure is a good medicine for the failure of regularity, but when you have a good medicine, when you're not sick, you don't want it to do anything, right? So if regular does nothing, that is tight closure is a closure operation, which I'll start out by talking about ideals. If you're in a regular ring, the tight closure of the ideal is the ideal. Okay, so if R is regular, I'm going to use this asterisk or star for the tight closure for all I. So just when you don't want it to do anything, it doesn't do anything. Now, the funny thing is, there's a lot of feeling that tight closure is hard to compute. I say no. Just think about regular rings. And in fact, one of the most important things about tight closure, even if you weren't interested in other rings where it's not just the ideal, if you're only interested in regular rings, it's still a very valuable idea. And the reason is that in a regular ring, it gives you a criterion for membership in an ideal that's a lot weaker on the face of it than being in the ideal. So it's not on my top 10 list, but so let's say nobody had ever defined ring, only regular ring, or people worked exclusively with even, say, polynomial rings. Tight closure would the idea of it would still be valuable, because and what's happening is you can sort of see that the element is almost in the ideal in some sense, which I'll explain. And tight closure theory tells you it's in the ideal. So even though it's not doing anything, it is telling you something as a criterion for membership in an ideal. By the way, I got the idea from an email from Bernd Sturmfels that if this wasn't very elementary, somebody would come out with a hook and pull me off the platform. So my apologies to, I know there are many experts on tight closure in the audience who are patiently listening to this. But I am trying to keep this at a level suitable for people who have never seen anything about it before. Okay. Well, I'm going to tell you a bunch of things about tight closure in more detail before I tell you what it is. I'm not going to define it for a while, because I want you to be, before I subject you to the definition is the hardest part. You have this complicated definition. It's hard to absorb. It's hard to see why anybody would ever define such a thing. And the only explanation for that I can give is the uses. It's very useful. And once you get past the hard definition, all the proofs are very easy. Well, maybe not all, but a lot of proofs are very easy, as item number 11, or is it 10? But 11's prime, let's call it item. Primes are much better than other numbers. By the way, I forgot to tell you, this is the course number. 101 is also prime. Well, one thing that I wanted to do pretty early is compare tight closure, this mysterious operation, with one that you may be familiar with already, integral closure. Because I'm going to start out talking about the Briançon-Skoda theorem pretty early, and I'm going to prove it. I want to show you how easy the proof is with tight closure. So, by the way, you know, if you have a question or a comment at any time, feel free to interrupt. Does anybody ever do that in these introductory lectures? Or you don't have to save your questions for the end. Now, I didn't say frivolous questions. I'm the only one who gets to be frivolous here.
That's not a frivolous question. Tight closure, if everything is tightly closed, is the ring regular?
No, I'm sorry. Yeah, it is not. And I will spend a fair amount of time on that. Sorry, I misunderstood that there was a serious point under the frivolity. In fact, let me just say right off the bat that suppose you take the polynomial ring in Mn variables. So, in other words, think of adjoining the indeterminate entries of a matrix, and then you divide out by the ideal of t size minors. So this is the ideal generated by the t size minors of the matrix. Then every ideal is tightly closed. But unless t is 1, or t is bigger than the size of the matrix, one of the sizes, this won't be a regular ring. So it's not usually regular. Okay, but I was going to say something about integral closure. So I'm going to give you a couple of characterizations of integral closure. And I'd like to think about mainly nice rings throughout these talks. So if you want to think about just finitely generated algebras over a field and their localizations, that's fine. Certainly, everything that I'm going to say is OK. So OK for localizations of finitely generated algebras. Over an excellent local ring. And if you don't know what excellent is, this includes all of, yeah. Well, since I haven't even said what I'm talking about yet, but yeah. Yes. Tight closure at the moment remains undefined for rings that don't contain fields. It's a big mystery whether there's even something that has the same properties. It would solve a lot of problems if there is. So I don't really want to worry about technical hypotheses in these talks. I'll be more careful in the written version than I will be in this version. But if you assume this, then I don't think there'll ever be a problem. The other thing is, for both tight closure and integral closure, you have the following fact. So this is tight closure. Bar represents integral closure if and only if this is true mod P. That's a capital P for all minimal primes P. Of the ring. So that means that for a lot of purposes, the main case is the case of an integral domain. You can reduce a lot of problems to looking at them mod all the minimal primes. So really, I'm going to focus on the case of domains in giving definitions and in talking about various theorems. And when I prove things, I'll generally prove them only in the domain case. And I would like you to know, though, that it's very easy to do the more general case. It's just not something I want to bother with here. Oh. Well, what use is it then? Is there one in between? Yeah. Okay. Oh, then you can use it to hide this one. So I should make all my errors on this board. Exactly. Okay. Okay, so in a domain, so I'm going to just look at the Noetherian domain. And of course, for integral closure, I don't need to worry about whether there's a field in it. So one criterion for whether something's in the integral closure these maps are supposed to be homomorphisms, where V is a valuation ring. Let's call it F. F of X is in IV. So one way of characterizing integral closure is just that if you try to, maybe R is complicated, valuation rings are simple. If you try to test whether something's in an ideal by looking at all mappings to valuation rings, and you get an affirmative answer, Well, it turns out the element doesn't have to be in the ideal. It only has to be in this integral closure. That's a characterization of it. And, but I want this. All right. And when R is Noetherian, this is actually a definition that works whether R is Noetherian or not. But when R is Noetherian, it's sufficient to look at you don't have to look at all valuation rings, just discrete rank 1 valuation rings, which Noetherian valuation rings, which I'll refer to as DVRs. And I guess there's an eraser over here. Wait, there's a middle one that comes down. And also, when R is a domain, one only needs to look at discrete valuation rings that contain R. So it's to be in the integral closure, it's sufficient if it's in IV for all discrete valuation rings containing R. So that's one characterization. A second characterization is that X is in the integral closure of I if it satisfies an equation actually I want to call that R1. With R sub j in the jth power of the ideal. So, and by the way, this does imply that X is in the radical of I. Because all these R's are in the ideal, so you get that X to the nth is in the ideal. Oh, let's leave the list. And a third characterization is that X is in the integral closure of I if and only if there exists C not equal to 0 in R, which, remember, I'm assuming is a domain. If I didn't have a domain, I'd want to keep C out of all the minimal primes. But let's just focus on the domain case, such that C x to the n is in I to the n for all sufficiently large n. Actually, you can say for all n. It doesn't, either one. Or for infinitely many n. They're all equivalent in this case. So a single C, but it's working for all n. And this is my favorite definition of integral closure. This is, by the way, this is for Noetherian, the Noetherian case. Because it resembles a bit, quite a bit, the definition of tight closure. And you'll have to be patient. I'm nowhere near the definition of tight closure. Now, the Briançon-Skoda theorem says and by the way, I'm not attempting to do anything in its greatest possible generality. So this is a minimalist version. Their theorem was proved, and they did it in the analytic case. But because you've done that using various tricks, you can get the case where there's a field of characteristic 0 in the ring. And what it says is that, so in their version, if R is regular and equal characteristic 0, so containing the rationals. But this is not needed, as you'll see. And I has n generators. Then the integral closure of I to the nth power is contained in I. This is and that's, at first glance, a very mysterious theorem. There are now lots of proofs of it by different techniques.
When you say R is regular, are you assuming that it's local?
It's not needed because of course, it's okay to say it in the local case, but the local case implies the global case. Okay, if you had it's okay globally. Let me give one example of integral closure. One thing with that equational characterization, notice that if x to the n is in I to the n, that's already enough to put x into the integral closure. And let R sub n equal x to the, or minus x to the n, I guess. Right, and you have the equation x to the n plus R sub n equals 0.
C equals 1 is your favorite definition.
Well, infinitely, yeah. But you don't need a theorem. I mean, so, for example, if you take the ideal generated by u to the n and v to the n, this is just in any ring whatsoever, and you look at any monomial of degree n, and look at the nth power of it, that's u to the nth to the I, b to the nth to the j, because very luckily the ring is commutative. And for that ideal, that puts it into I to the I times, this is I. And so that implies that the integral closure of u to the n, v to the n contains all monomials of degree n in u and v. So the integral closure of an ideal, even in a regular ring, I mean, you could take in the polynomial ring in two variables this ideal and look at its integral closure. Then it would be exactly this. But typically, the integral closure of an ideal is substantially bigger than the ideal, even in a regular ring. Now, I did want to mention, I'll put the exact theorem in the notes. In fact, enough of the notes are written that I can tell you it's already in there. This Briançon-Skoda theorem, their proof, which was used an analytic criterion of Skoda for membership in an ideal. And just so that you'll understand that the tight closure proof is easier, I thought I would say something about that criterion. But I'm not going to write it down exactly. The idea is you have a nice neighborhood. Think of the ring of germs of analytic functions in n variables in Cn as the ring, which can be thought of as formal power series. So we're interested in Briançon-Skoda for R. And the idea is that omega is a nice neighborhood of the origin here. Because you actually, in proving that something's an ideal, Skoda's criterion does it by sort of finding the functions. And so he's constructing holomorphic functions. And you don't do that in the ring of germs. You do it on some neighborhood of the origin. A small, but nice is technically pseudo-convex, but I don't really want to talk about several complex variables here, so I'm not going to do too much detail. And I guess well, that's all right. I think it's been up long enough. And let's say f and g1 through gk are holomorphic on omega, and x is the common zeros of the g's. That's where they all vanish. And I'll say I'm not going to write this down precisely, but if you look at the integral of f to a certain power, I mean, it's completely specific, but I'm just over the sum of the squares of these guys to a certain power, certain other power. And now there are other things here which I'll just call stuff. I will give the details in the notes. And you integrate with respect to Lebesgue measure. And if this is finite, by the way, there are actually uncountably many forms of the theorem. And this implies that f is summation gj hj with the hj holomorphic on omega. Here I threw out x because the g's vanish there, so this integrand isn't defined on x, but it's a measure 0. And depending on the form of the theorem, there's a plurisubharmonic weight function that comes to the statement. But when you're working in the ring of germs, it doesn't matter what it is. I mean, it's sort of, in one version, there's a certain Laplacian. I don't know. It's analysis, believe me. I spent a long time understanding this because when I first saw the Brianstone-Skoda theorem, no other proof was known other than this analytic proof. And heuristically, what's the point? The point is what this is telling you is that if all the g's are small, then f is small, usually. Okay? And that's what if f is in the ideal generated by the g's with holomorphic coefficients, you'd expect it to be small when all the g's are small. And the finiteness of this integral, which I haven't written down specifically, but is telling you just that in I mean, this is similar in a way to Hilbert's Null-Stellensatz, which, you know, when you're working with actual polynomials on complex n space, it's saying, Hilbert's Null-Stellensatz says that if f vanishes when all the g sub j vanish, that implies that f is in the radical. It has a power in the ideal. So it's in, right? This is Hilbert's Null-Stellensatz. It's much more subtle, though, to give a criterion that puts f in the actual ideal. Okay? And this finiteness of this integral. Now, the proof of this theorem is a 40-page paper of Skoda's, and then Brianstone and Skoda used it to prove the Brianstone-Skoda theorem, which I guess Brianstone had conjectured. So I think of this proof as kind of hard, but maybe that's just because I'm an algebraist. So now, by the way, when am I supposed to stop? At a quarter of?
Quarter of.
Okay.
Is it clear from this criterion that there's any sort of effective Null-Stellensatz using this criterion? Have you ever tried to?
No, and you know, this condition is sufficient to be in the ideal, but not necessary. And also, you know, because I haven't written out the integral explicitly, I've sort of hidden that that there are a lot of different forms of it. You know, there are many integrals that work, basically, because there's you have to put in an exponent, you know, a factor into the exponent that's bigger than 1, and any number bigger than 1 works to give you a sufficient condition in one form of it. In another form, you have to multiply by Laplacian of a certain function. So
there are easier analytic
proofs. Yeah, I know. But this was the first proof. And I should say, I gave lectures in the late 70s in which I challenged algebraists to give an algebraic proof of the Brianstone-Skoda theorem, and the challenge was met. First, Lippmann and Tessier proved it in a special case, and then Lippmann and Satté in the general case, even in regular rings, even if mixed characteristic. So there were algebraic proofs before the tight closure proof. I still claim that the tight closure proof has virtues that none of the other proofs have. And so let me see whether I can convince you of that. Now, at this point, I'm more or less forced to give the definition of tight closure, sort of against my will. But I guess you can't really prove something with tight closure if you don't have the definition. So, and the definition, there is a definition for rings of characteristic 0, and I will try to talk about it a bit, but most of the theory really takes place in positive characteristic P, and then there are sort of standard tricks for getting characteristic 0 from characteristic P, which I think I'll only have limited time to talk about. But I'm going to talk mainly about characteristic P. So from here on in and for a while, R is the theory and characteristic P. And when I write P, P is always a positive prime integer. So when I talk about characteristic P, P is never 0, okay? It's always a positive prime integer. And I'm going to make the convention that the letter Q is exactly the same as P to the E. So as E varies, Q varies. So I guess. And now I'm going to give the definition in the domain case, because I already said you can test mod any minimal prime. So in some sense, that reduces the question of what tight closure is to the, I mean, in a very clear sense, it reduces it to the domain case. So let's say R is a Noetherian domain. X is an element of R. I is an ideal of R. I had an eraser here somewhere. Oh, well, it's here. Okay. Then X is in the tight closure of I. If there exists C in R and not 0, such that Cx to the Q, now I have to define this, is in I bracket Q. For all Q, remember this is Q of the form P to the E. I can write sufficiently large. In the domain case, all Q is equivalent. It doesn't matter whether you say all sufficiently large or all. You can adjust C to take care of the, if you were missing a few of these, you could pick a C that would adjust for it. A different C. So the C in the tight closure test is allowed to vary with the ideal and with the element, but it has to be independent of Q. Now, what is I bracket Q? Let's leave that. I bracket Q is the ideal generated by the qth powers of the elements in I. And notice that if you have summation R nu, I nu, and you raise it to the qth power, because the Frobenius is a ring endomorphism, you get a linear combination of the qth powers of the I sub nu. So here, you only need to use generators of I. You don't have to use all the elements. But be careful, it's not just the set of qth powers. That's not an ideal. You have to take R linear combinations of qth powers. Okay? So this I bracket Q is contained in the ordinary qth power. But it's very different. If you take generators, here you just get, let's take generators, I'll call them F1 through Fk. Over here you have things like Fj to the Q. But over here you have, F1 to the A1 up through Fk to the Ak, where the sum of the A's is Q. You get all monomials. Here you're not getting all monomials. You're only getting qth powers of elements. That's very different. The bracket qth power is much smaller than the ordinary qth power of the ideal. Okay? So a couple of things we can say right away from this. So I'll just say these are easy, and well, that's very easy. This is likewise very easy. This is slightly less easy, but it's not difficult. So this is a sort of closure operation. And let me say heuristically why you would think that if an element satisfies this condition, then it's close to being in the ideal, because that's the feeling you should have about it. So one thing that I want to take as sort of axiomatic is that if we have the situation of a module finite extension, and I is an ideal of R, it can happen that you have an element of R that's in the expansion to S and not in the original ideal. So R gets into the expansion to S. It's in the original ring, but it's not in the ideal when you look in the original ring. The extra coefficients from S help. Okay? Then I want to say that in this situation, one feels R is almost, whatever that means, in I. Okay? Now, if you don't believe that, then you'll just have to disagree with me. But now look what's happening in this definition. If you take qth roots, we have an equation like this, C r to the q. I'm going to let I be generated by f1 through fk. And now this is summation rj fj to the q. And so in the ring with all qth roots adjoined, I'm assuming a domain. So I can say this, C1 over qr is summation rj to the 1 over q fj. And, you know, R with these elements, C1 over Q, R1 to the 1 over Q, through RK to the 1 over Q, adjoined, is module finite over R. And this is the ideal generated by the F's in R1 over Q, or in this ring. Let's call this thing S. So this thing is in I expanded to S. So what we're getting here is that C1 over Q R is almost in I. But we're getting it for all Q. Okay? Now, what happens when Q is very large? Well, in some weird sense, C1 over Q is approaching 1 because the exponent is approaching 0. C to the 0 is 1. Okay? Not really. I mean, I don't have some topology in which C1 over Q is approaching 1. But in a vague heuristic sense, you can think of this element as close to 1 when Q is very large. So I have something that in some weird vague sense is close to 1 multiplying R to give an element that's almost in I. And so almost in I should be almost in I also, right? Well, whether almost in is transitive, I don't know. But for an introductory explanation of why this condition might be thought of as telling you that the element is almost in the ideal, this is as well as I can do right now. So you should think of elements that are in the tight closure as almost in the ideal. So now I'm set to prove a theorem. So I'm going to call this Briançon-Skoda. Actually, I guess it's in the first main paper that Craig and I wrote about tight closure. And it says that the integral closure of I to the n. Remember, the Briançon-Skoda theorem says in a regular ring, this is in I. Now, I'm not going to say that. Instead, I'm going to say it's in the tight closure. But notice, as I asserted earlier, we haven't proved it yet. The tight closure is the ideal if the ring is regular. So this implies Briançon-Skoda for regular rings.
For n equals the number of generators.
Yeah, I should have said I is n generated. Thank you. I'd have figured it out when I tried to do the proof for regular rings. Well, actually, containing a field of characteristic P. But by very general principles, once you know Briançon-Skoda in characteristic P, it turns out you get it in the equal characteristic 0 case. And I'll come back to that. So by certain standard tricks, you actually get Briançon-Skoda in greater generality than the original theorem, but not the generality of the Lippmann-Saté theorem, because their result includes the mixed characteristic case where you have regular rings that don't contain a field. However, this theorem has certain virtues. I mean, this is in any ring. You're always in the tight closure, even if it's not regular, even if it's a horrible singularity. So this is, in some ways, stronger, even though we don't have mixed characteristic. Now, admittedly, I'm cheating because I still have to prove that in a regular ring, every ideal is tightly closed. So I'm not really done with the two-sentence argument I'm about to give. But the proof of this fact, that the integral closure of the nth power is in the tight closure, is extremely simple. It's so simple that it's almost embarrassing. But having already accused analysts of having lice, I guess I can face down the embarrassment of giving an easy proof. So let's say so we can assume R is a domain. You can work mod every minimal prime, both with integral closure and with tight closure. And now let's say U is in the integral closure of the nth power of I. And remember, we're going to need to use that the ideal has n generators. And remember, from the third characterization of integral closure, this is telling me that Cu to the m is in I to the n to the mth power I could say for all m or for all large m. I'll say. With C not 0. And of course, I can restrict m to be a power of p. It's actually not really a step, even. So this thing is f1 through fn to the nq power. Now just think for a minute about a monomial in the f's where of degree, total degree, nq. If the total degree is nq, what can you say about these a's? Could they all be q minus 1? Well, if they were all q minus 1, the degree would be n times q minus 1. Right? If they're all at most q minus 1, the biggest this degree could be would be n times q minus 1. But it's degree nq. So what that's telling you is that one of these exponents has to be at least q. They can't all be smaller than q. It's the pigeonhole principle. If you try to put nq things into n slots, you've got to put at least q of them in one of the slots. Otherwise, you get stuck. Oh, but that is I bracket q. That's the proof. It's for all q, c to the q. Okay? So if we had also the fact that ideals of regular rings are always tightly closed, we'd be done. So to finish up, I have slightly less than 5 minutes, but I think I can do it. So this is a theorem. And, all right, so suppose C is, I'm going to assume R is a domain. A regular ring is actually a product of domains, and it turns out you can look at each factor separately. So suppose R is a domain. C is not 0, but cu to the q is in I bracket q for all q. I want to show that u is actually in I. Now, a slightly different way of thinking about these bracket powers is, let's introduce the Frobenius endomorphism. So I'll call that F. And F composed with itself E times maps R to R. And f of r is r to the p to the e, which, remember, is the same thing as r to the q today. And here's the nice thing about regular rings. F is flat. Now, so when a regular ring is viewed as a module over itself using the Frobenius endomorphism, it's a flat module. And I don't want to do all the details of that, but you can come down to the local case And then you can get to the complete case. And in the complete case, the ring looks like this for some n. Maybe I should use a different letter. Let's call it k. And so this is the field of all pth powers. And the Frobenius map is like the inclusion of this ring in k double bracket x1 through xn. And so you're doing two things. You're enlarging the field, and it's easy to show that that's flat. And then you're joining pth roots of these elements to it. And it's easy to show that that, in fact, is free. So, so by reducing to this complete local case, I'll just say it's easy. Frobenius is flat for regular rings. It actually characterizes regular rings in characteristic P, in case you wanted to know what regular really means. In characteristic P, it means Frobenius is flat. And I'm out of time. So I'm going to quit, although we're only a couple of minutes short. I don't want to run over. So I'll continue. I'm getting another lecture this morning, right? So you'll have to hold your breaths. It's fast?
It's a little fast.
Okay, 3 minutes only then. Thank you. So it's a little lemma that says that if S is flat over R, I is an ideal of R, and let's say X is in R, then IS colon X over S is I colon X over R expanded to S, where J colon X equals all elements of R multiplying X into J. I'm going to leave that as an exercise. That maybe I'll give you a hint. Tensor with S. The kernel is like I colon X. Sorry, let's do one more. But anyway, so this is an easy fact about flatness. Now, I bracket Q is the same thing as I expanded to S. If we put the Frobenius here and think of the second copy of R as S, IS, then remember that S is R and figure it out, is I bracket Q. So this tells you that I bracket Q colon X to the Q over R, for R regular, is I bracket X to the Qth power. And now, I guess I should have been using U instead of X. So here, what we have here is that C is in the intersection of I bracket Q colon U to the Q, which is the same thing as the intersection of I bracket U colon Q. And if this is a proper ideal, the bracket qth power is contained in the qth power. But if you have a proper ideal of an Ethereum domain and you intersect all the powers, you get 0. That's an easy theorem. That's going to be 0 unless I colon U is the whole ring. But that says U is in I. Now, since C is not 0 and it's in this intersection, the intersection can't be 0. So I colon U has to be the whole ring, and therefore U has to be in I. So that's the proof that in a regular ring, every ideal is tightly closed. Okay. Thank you.